Okay, so welcome back, everybody. So yesterday we left off right when we were about to start doing some examples. So I think it's probably a good idea to have a look at where we stopped. So we had written the general form of this input-output model we discussed. So it looked like this. We had, and we gave names to all these quantities. So we had our production vector, M is the consumption matrix, D is the external demand vector, M times P is itself a vector that is the internal demand vector. And we said that an economy was called open if the external demand was non-zero, meaning not the zero vector, and closed if it was in fact the zero vector. So typically we are going to be talking about open economies. Closed, that's a very special thing mathematically, so typically we're not going to be talking about that. Although we will cover it when we talk about these all of these cases. So anyway, this was our setup, and we mentioned from that point we mentioned that, well, if we just start solving this, right, rewriting this equation, because there's this production vector P appears on both sides, and this is the thing that we are going to be solving for typically. So M and D will be known, right? So the consumption matrix and the external demand vector will be known, and we're solving for P, this production vector. So rewriting this, you might notice is similar to an algebraic move that we do when we're talking about eigenvalues and eigenvectors. So we get this quantity here. So matrix times vector that we're solving for is equal to some right-hand side vector. This is an AX equals B, right? This is AX equals B. Hey, our favorite equation, right? The equation that linear algebra is centered around. So we're happy here. Okay, and we're solving for this vector P here. So there are four cases. I broke them like this. Really, there's only a couple cases. So basically, I minus M is either invertible or it's not, right? Statistically speaking, it is more likely to be invertible, right? Because a matrix is more likely to be invertible. And the reason for this is just consider like all the determinants it could have, right? So a matrix could have any determinant that you want, and it will be invertible so long as its determinant's not zero. So there's only one value of the determinant that is not allowed. Here, all other values are perfectly fine. So in that sense, statistically, a matrix is invertible. Now, you know, that's that's not the best way of saying that a matrix is invertible without actually checking. No matter how true that may be, there still are plenty of matrices that are not invertible. So, fortunately, you got to check. But just speaking, you know, overall, right? Statistically, matrix is more likely to be invertible. So, all those are things. If we're talking about picking a matrix out of a hat, right? So, in the second case, we have an invertible matrix, but the external demand vector is 0. In this case, the production vector is 0. So, okay, that's our unique solution in that case is just the trivial solution, 0 vector. So that's not so interesting. So having a unique solution, that is nice. And if we're to believe this previous analysis that I just spent time saying, this is going to be the most likely case. In the event that the matrix is not invertible, then this might have none or infinitely many solutions. We know that's not saying much in terms of linear algebra. This is just how it goes when you have a non-invertible or a singular matrix here on the left. Of course, if it's not invertible and the external demand vector is 0, then there are infinitely many solutions. Because we know it has at least one solution, because this is now a homogeneous matrix equation. So since it has one, it has to have infinitely many, because unique is out, because it's singular. Okay, and so then the primary cases here, of course, are it's invertible or it's not, right? Those are basically the two big cases. These are the case where you have a closed economy, okay, and what that means. All right, so let us start with an example where we actually see how this works. And the example that I'm going to use is actually going to be the one that I wrote out when we were formulating all this stuff yesterday. It's going to be this one. So here is going to be the consumption matrix that I use. Okay. So using this, this is M is the matrix 0.1, reading row-wise, 0.15, 0.12, 0.2, 0, 0.30, 0.25, 0.40, and 0.20. This is my M. And let's say that my external demand vector is the following: 100, 200, 300. So this indicates the demand in my units, right, of the products in question. Okay, so this is demand for product. This is the external demand for product 1, external demand for product 2, external demand for product 3. Okay, so in this event, you might have already noticed this. For this M, what I'm looking for is I minus M. I minus M is going to be invertible in this case, which we can just check by computing its determinant. But you can check here that I minus M is invertible. So that my solution, to recall, right, I have rewritten this input-output model equation in the following form, so that my solution to I minus M P is equal to D is P, which is I minus M inverse times D, which is the 1-by-1 identity, or sorry, the 3-by-3 identity. There it is, minus my matrix M. I'm not going to rewrite that. Inverse times my vector D. You can compute this and see that this is equal to the vector 281.30, 464.86, and 695.34. So, what does this mean? Well, this means in order to satisfy the external demand and the internal demand required to produce enough units all around, I should set my production to this. This is exactly what I should set my production to in order to satisfy these things. Okay. Now, if we think about what this means, so notice most of my demand, or I should say most of my production, is going to meet the internal demand. Well, how can I tell that from this? Well, if this is what I'm claiming I need to set my production at in order to meet both the external demand and the internal demand required to produce all of these things, then from this production vector P, I should be able to see what is required for the internal demand. In fact, I can see that immediately, right? Just by subtracting off this external demand, right? So P minus D should tell me exactly that. So note that P minus D for this example what is this? This is that vector I just found, P, so 281.30, 464.86, 695.34, minus my external demand vector D, which is just 100, 200, 300. And what I get is that this is 181.30, 264.86, and 395.34. So what is this? Well, this is how much is being used up internally, right? But, I mean, this is just our internal demand, right? To remind yourself that this is, in fact, the internal demand, let's go back to our, where is it? Here it is. What is P minus D? Well, from this equation, P minus D is just M times P. But M times P is the internal demand vector. So, of course, right? Now, I mean, obviously, you know, how I've defined all these things, this would make sense even if we didn't know this. This would make sense that that's what this is giving you. You're subtracting off the external demand. What is left for your production is what you're producing for internal purposes. So this is your internal demand. And so this is how we see that, oh, more is being used internally or is being required to meet the internal demand, right? So the internal demand is much higher than the external demand here. What does this mean? In a sense, that this means that this economy is not very efficient. Right? It takes a lot of input to generate, relative to the amount of input, not so much output, right? So this is an inefficiency. Okay, so let's see an example of a more efficient economy. A more efficient economy here is going to have a consumption matrix with smaller entries here. Remember what the vectors of, or the column vectors of the consumption matrix are. These are the consumption vectors. And the way that we interpreted that is that the jth column of M is the jth consumption vector, and it contains the necessary input from the sectors for sector J to produce 1 unit of output. Right, so this you could just read off these things from looking at the consumption matrix itself. So let's let our consumption matrix be the following. So I'm going to read row-wise again: 0.01, 0.002, 0.04. The next row is 0.02, 0.004, 0, 0, 0.01, and 0.02. You like seeing zeros here, especially because, remember, in the context of these sectors producing products, it means that one of the sectors doesn't rely on one of the other sectors to make its product, right? Which is nice, right? That this there's some self-sufficiency here of a sector or two. And let's say that our external demand is the same. So same external demand for these products. Okay. Again, you can check that I minus M is invertible. Okay, remember this is also the more common case. In this case, our production vector is I minus m inverse times d, which in this case, for this particular example, is 113.873 to 03.09 and 308, can't write today, 0.195. So that this is my production vector, this is my solution to this thing, which means I should set my production to this if I want to meet this external demand and all of the internal demand that is required to produce all of the units, right? Both the ones that are needed internally and the ones that are needed to meet this external demand. So notice here that P minus D is much smaller if we thought about like the magnitude of this vector. This is much smaller here. This would be 13.873, 3.09, and 8.195. What does that mean? Well, this means that the internal demand, right, is very small relative to the external demand. So this is a much more efficient economy. So much more efficient compared to the last example. Okay, so most of the production is going directly to the external demand. So that is good. That's good. Okay. Now, you might have noticed, right, that in these examples, right, we ended up with production vectors that were non-negative. They had non-negative entries here. But that doesn't always have to be the case, right? So you might say, well, surely that's the case whenever you have some kind of reasonable model for what's going on. Yeah, you might say that, although this can happen. This can happen even in case where you do have some kind of reasonable model. Maybe the first example might not seem as reasonable, and then I'll give you a second one. So first, here's an example to see that the entries of P need not be non-negative. Let's set M to be the matrix. Again, reading row-wise, 0.3, 0.2, 0.1, 0, 0.2, 0.2, 0.1, 0.3, and 1. Okay. Now, if we use the same, we will use the same external demand vector. And if we do that, then again, I minus P is invertible. I'm just going to immediately write this out here. Or sorry, I'm not I minus P, I minus M. I minus M is invertible. And if I compute what this is negative 611.11, negative 796.3, and negative 3685.2. All right, now considering that this is supposed to be telling me what I should set my production at for each of these units or each of these products, what is this telling me? The fact that these are negative, right? That doesn't really seem to make sense, right? Based on how we have set up this problem, what we're supposed to be modeling here. But what is it that is happening here? So question, what's the problem? You might note that the entries of the consumption matrix aren't strange in the sense that there's no like negative numbers there showing up. So what is going on here? Well, you might notice this entry here being a 1. What does that mean? This means, because this is in the third column, sector 3 requires 1 unit of product 3 to produce 1 unit of product 3. But the thing is that sectors 1 and 2 also require some amount of product 3. Right? So just to make 1 unit of product 3, sector 3 requires an entire unit of product 3. But then there's more of product 3 that is required by the other sectors to make sure that this production happens. And so this means that there's no possible way for this to be satisfied, right? So no possible way for the internal demand to be satisfied. So no possible way for external or internal, in fact, demand to be satisfied. Hence, the strange, I'll put strange in quotes here, the strange answer. Now, you might look at this and say, well, just, just don't. Like, if you're starting with the consumption matrix, and you have an entry that is a 1 here, and, there's not zeros elsewhere that indicate that no, basically no other sector requires more of that product, so that at least it's possible to meet the internal demand. But this isn't always the case. It's not something like this that is the only problem. Okay, so here's another example. This showing that 1 entries are not the only problem. Here, check what happens. Use the same external demand vector. Check what happens if your consumption matrix looks like this. So again, reading row-wise, this is 0.3, 0.7, 0.1, 0.8, 0.2, 0.2, 0.1, 0.1, 0.3, 0.1. There we go. So I'm not going to check this one for you, but you check this and see that, in fact, this has a similar type problem. And also think about why that is. Think about why that is and why it's not enough just to avoid the entries of 1, but you might think about what reading these rows tells you, for instance. Okay, and whether or not that has anything to do with it. Okay. So, everything we did there was showing you how it works when I minus m is invertible. So now, just for completion's sake, let's talk about when I minus m is not invertible. So let's do the case that I minus m is not invertible. Okay. So how does this work? Well, again, this is not going to be as common as the previous case. So this is typically not going to be something you're dealing with as much. But let's go back to our equation. So there it is. And I minus m is not invertible. So we have two possibilities, either no solutions or infinitely many solutions. That's one possibility. Infinitely many solutions is the other possibility. Okay. Well, let's see some examples, right, showing that either of these cases is possible. And there's a lot of ways in which this could happen, right? So, we didn't put any size restrictions on M. Even if we have a 2 by 2 matrix, very quickly we can see both of how this could happen. So, for instance, if my consumption matrix is 0.1001, then I minus M is 0.9000. This is clearly not invertible because its determinant is 0. So not invertible. Consider two separate external demand vectors. Let d sub 1 be the vector 100, 0. So there's a demand of 100 units for product 1, 0 units for product 2. And let d sub 2 be the external demand vector 100, 100, so that there's a demand of 100 units for each of the products here. Okay. Note, we get both of these cases here depending on which external demand vector we pick. Right? So, I minus m times p is equal to d sub 1 has infinitely many solutions. I minus m times p equals d sub 2 has no solutions. Okay, you can try to solve, say, this one to see what happens. Or you could actually just, even if you didn't really understand how matrices work or how solving matrix equation works, if you understood the economic model side of things, you could also see why this is not going to work, or rather why this one doesn't have a solution. Okay. Now, it doesn't really make sense to try to break down every possible way in which this could occur, right? So rather than that, we're just going to kind of focus on one particular case. We'll do it for a closed economy, and that will allow us to say some things about how this works. So first, let's just see what happens in a closed economy. So let us see what happens when I minus m is singular, that is not invertible, and we're in a closed economy so that the external demand is a zero vector. Okay, in this case, my equation that I'm solving becomes I minus m times p is equal to the zero vector. It's now a homogeneous equation. But of course, this is the same as the equation I times p is equal to m times p, or rewriting it in maybe a form you're more used to seeing. MP is equal to P, or writing it in an even more suggestive form, M times P is equal to the number 1 times P. Now, why did I write it like that? Well, this is to show you that this happens exactly when 1. You can go back to our first day of lecture when I went over this review material a little bit. Here, right, what does this equation mean? This means that 1, or I should say P, is an eigenvector of the matrix M corresponding to eigenvalue lambda equals 1. So what does this mean? This means P is a solution, and also any scalar multiple of P is also a solution. Now that is because when you scale an eigenvalue by a scalar, it remains an eigenvalue for that same matrix corresponding to that same eigenvalue. Sorry. When you scale an eigenvector, I think I said this right the first time maybe, but just to repeat myself. When you scale an eigenvector by a scalar, it remains an eigenvector for that same matrix corresponding to the same eigenvalue. Okay, you can prove this directly in a couple lines just based on the definition of an eigenvalue eigenvector pair. Okay, so for instance, eigenvectors, this is usually stated in linear algebra that eigenvectors are not unique, right? When you found an eigenvalue, finding an eigenvector for that eigenvalue, the eigenvector is not unique. You can scale it. You can also, depending on the dimension of its eigenspace, you can do other things to it potentially, but you can definitely always scale an eigenvalue no matter what, even for a dimension 1 eigenspace, and any eigenspace has to have at least dimension 1. That's as low as it can go. You can always do this. You can always replace it with a scalar multiple and it remains. So that's what this means. Okay. Now, think about what kind of restrictions this places on what's going on. So, not only does I minus m need to be singular, which is already a less common thing, but also m itself has to have 1 as an eigenvalue. All right, which is, again, that's a very special thing, right? Like, there's many eigenvalues a matrix could have. It specifically having the eigenvalue 1, that's a special thing. So this is even more restriction. If I look at the example as follows, let M be the matrix, reading row-wise 0.1, 0.4, 0, 0.2, 0.4, 0.9, 0.7, 0.2, 0.1. This actually has eigenvalue 1. And eigenvector P corresponding to it is, again, I'm not implying that this is unique, so however you go back to, Math 240, find eigenvector, your favorite method that you used in Math 240, or maybe, maybe you took 246, so you have used like Cayley Hamilton as a shortcut for 2x2s or something, right? So whatever's your favorite method for finding eigenvectors here, just the usual way is fine. This eigenvector that we found is 0.3605, 0.8111, 0.4606. Okay. And in fact, which means some other solutions are as follows. Here's one. Let's multiply the thing by 10. And another one. And another one. What does this mean? I can keep doing this. What does this mean? If I can do this, right? This means this is an economy that can essentially scale up simultaneously, however you want in this way, right? So this is a very special thing. This economy can scale up everything simultaneously. This is, and of course I didn't have to stick to just multiples of 10 here. I could have multiplied by any scalar multiple I wanted to. It was just that's the easiest thing to do when you have numbers like this. This is an economy that can scale up everything simultaneously. This is a very special thing. Of course, again, we're doing this in the case where our D is 0, right? That's what we assumed here at the top. So there is no external demand to be met, so this is all just purely to meet the internal demand. So there's no external demand being handled whatsoever here. Okay, so again, this is a much more special thing. This is also consequently not going to be something that comes up as frequently, but now you've seen it, and this is there's no need to break down the cases here. When you are in a case like this, right, you would analyze it on a case-by-case basis, but this is not going to be something you're frequently going to have to do. Okay. Moving on. So now, what about this matrix I minus m inverse? So let's move back to the case where I minus m is invertible, our typical case, and look at what this inverse means. And what we mean by that is I want to be able to interpret this like entry by entry. So in this case, we have a unique solution, which is exactly this, right? This is our unique production vector that tells us what we need to set our production at in order to meet all the external demand and the internal demand that produces everything, okay? So how am I going to make this work? So first, for simplicity's sake, just with writing all this stuff down, and then we'll move to the general case later. Assume that M is a 3 by 3 matrix, which means D has 3 entries. I is the 3 by 3 identity matrix, just so that it makes this easier to write out. Okay, so we know that production must be set at this. Okay, so let us check what happens when external demand for product 1 changes by +1. So what happens when we increase the external demand for product 1 by a single unit? Okay. So the new external demand is the old external demand plus the vector 1, 0, 0, just to show that we have incremented the demand for product 1 by 1 unit. Okay, how does P change? Well, then this new production vector would be I minus M inverse times D new, which I'm just going to go ahead and skip and write this as D plus 1, 0, 0. Now, matrix multiplication in this way distributes across this parentheses so that I get I minus M inverse times D plus I minus M inverse times 1, 0, 0. But of course, I minus inverse times D is just P. That's my previous production vector. Plus I minus M inverse times this vector 1, 0, 0. But, this vector here, what is that? Well, that's easy to see what that is, right? So this is going to be some 3 by 3, right, in our case. And we did this specifically just to make writing this out by hand less tedious, okay? But what is this? This is going to select out what? This is going to select out the first column of this thing, okay? And so all this does is contain the first column of I minus M inverse. So maybe I'll write that out in words to really emphasize what it is that's going on here. So note I minus M inverse times the vector 1, 0, 0 contains the first column. This contains the first column of I minus M inverse, which means, well, what does that mean? Since this new production vector, that is the new production vector I get by incrementing the external demand for product 1 by 1 unit, the thing that I add to my previous production vector is exactly the first column of I minus M inverse, so that the first column of I minus M inverse means this first column of I minus M inverse indicates how the production must change in each of the 3 sectors if the external demand in the first sector changes by +1. That is for the first sector's product. Again, why is this? I get the whole first column, right? Whatever the first column of I minus M inverse is, because this one is picking out the entries in the first column. Everything else is getting zeroed out here. So the result of this multiplication is literally just the first column of I minus M inverse. And because I'm adding that to my previous production vector, I'm adding the first column of I minus M inverse. So that first column tells me exactly how the production must change in all of the sectors when I increment the external demand in the first sector by +1. Okay. So, to see this, let's say that I have a consumption matrix N that looks like this, 0.1, 0.15, 0.12. You might remember this matrix, right, that we started out with today. 0.2, 0, 0.3, 0.25, 0.4, 0.2. If we compute I minus M inverse, this matrix is, writing this row-wise again, this is 1.2660, 0.3128, 3072. Next row is 0.4375, 1.2850, 0.5473. Next row, 0.6144, 0.7400, and 1.6200. This is my I minus M inverse. Now, what does this mean if this column is getting picked out, right? When I multiply by the vector 1, 0, 0, it means that this column contains the info for how the external demand for product 1 changing by +1 units changes the production in each of the sectors. So, what this means is that if the external demand for product 1 changes by +1, the production in the 3 sectors must change by these entries, plus 1.2660, plus 0.4375, and plus 0.6144, respectively. Okay. Now, does that make sense, like relatively, that this would be the case here? Right, you can think about that. Whether these numbers seem to make sense based on what they're supposedly interpreting. Now, you may have noticed, and the reason that I wrote out all of the entries here is to say that, well, you know, I did this to see what happened when I increased the external demand for product 1 by 1 unit. But what if I had done the same thing, increasing the demand for product 2 by 1 unit? So that instead I would have this matrix instead. Or sorry, this vector instead. This, of course, picks out the second column of I minus M inverse. And so what this is telling me is the amount that production has to increase in each sector, respectively, if the external demand for product 2 increases by 1 unit. Again, notice this entry here. Okay. So that to interpret what's going on here with the entries, I don't have to focus on a single column. In fact, each of the columns tells a slightly different story here. It tells me what happens, right? So the third column is what happens, or how the production must increase in each sector if the external demand for product 3 increases by 1 unit. That picks out the last column. You may already see where I'm going with this, which is not only can I do this for any column, but actually each of the individual entries also have meaning on their own, right? Which is the specific amount the production needs to increase in that particular sector, given an increase in external demand for the product indicated, right? The corresponding product. And so I'm going to kind of tidy up all of that stuff in the form of some facts that we can rattle off here. So what are those? So fact one, we'll call it. So if external demand for sector J, that is the product J, right? The product that sector J produces. So if external demand for sector J changes by +1, then column J of I minus M inverse indicates how production must change in all sectors in order to compensate. Okay. But as we, as I indicated, as I hinted, actually we can do this entry by entry. So if the external demand for sector J changes by +1, then the ith entry of the jth column of I minus M inverse, of course, another way to say this shorthand would be the ijth entry of I minus M inverse, indicates how production must change in sector I in order to compensate. Okay. So this is a single entry is, if the previous thing contains the how production must change in all the sectors, what we mean by that is entry by entry, it contains exactly how it must change in each sector individually. Okay. And even better than that, you might say, well, that's great and all that we know what happens when it changes by 1, but frequently if we're going to update our external demand, it's not going to be in terms of 1 unit increments. It's going to be, oh, now the external demand for this product has changed by 5,000, right, or 5,720. Okay, it's not going to be just +1. So we need to know how to answer a question about changing the external demand, not just in increments of 1, but luckily for us, this is linear in how this works. So this change is linear in nature. Hey, that's exactly what you want to hear in linear algebra, right? In that, if external demand for sector J changes by, say, +k, where k is non-negative, but I mean, functionally this is going to be positive. We can simply scale column J by k to get the production change that is needed here. Okay. This allows us very quickly to determine how these things work. So these three facts combine to allow me to determine a lot about what is going on with this economy based on the entries of I minus M inverse. So let's do a quick example. I'm going to do an example of what we'll call a sparse matrix. What's a sparse matrix? A sparse matrix is a matrix that has a lot of zeros. Now, what counts for a lot might change in the context you're talking about. But so sometimes this will have a very specific meaning where there needs to be so many zeros, but let's let M be the following 5 by 5 matrix, so 0.200, 0.100, 0.020, 0.0600, 0, 0.04. I'm not going to keep writing extra zeros here. Understand? No, I'm just going to have this be 0 and have this be 0.07. Next, 0, 0.015, 0, 0.011, 0, 0, 0.022, 0, 0, 0.08, 0.0300, 0, 0.032, 0.01, and 0. Now, what is I minus M inverse? I'm not going to write out this full thing. You can see it in your notes. I'm just going to indicate the fourth column here specifically. The fourth column is 0.0216, sorry, 0.0025, 0.0110, 1.0009, and 0.0110. Then you have a fifth column. So this is my fourth column, which indicates what? This means that if external demand in sector 4 increases by +1, then production in sector 1 needs to increase by +0.0216, sector 2 by +0.0025, and so on. All right, you get the idea here. Okay. Now, notice in all of these examples, both in this example, where we notice that the production for sector 4 has to increase by more than 1. Here, in this previous example, we saw that in column 1, the production for product 1 corresponding to external demand increasing by 1 had to go up by more than 1. Same here for product 2 when external demand for product 1 or product 2 increased by 1. Same here for product 3 when external demand for product 3 increased by 1. The way in which each of these is greater than 1, does that make sense, right? Maybe the past examples make you a little worried about entries of more than 1, but remember that was entries of 1 or greater in the consumption matrix M. This is I minus M inverse. But does this make sense? Well, yeah, this makes sense, because what does this mean? It means that the production in that sector has to go up so that it produces enough to cover the new external demand for the product 4 that it produces, plus enough to cover the internal demands of all the other sectors, because those other sectors require some number of product 4, right? Some number of units of product 4. And so in order for all this production to keep on churning out, in order to accommodate this increased demand, this has to go up by more than 1. So that makes perfect sense here. Notice that if it changed by, if the external demand increased in sector 4 by, say, -2, that is, it went down by 2 units, which absolutely can occur, right? Sometimes the external demand would decrease. How would I see how this should be impacted, or how the production should be impacted here? This would be, right, production should be impacted by -2 times column 4. I'm not going to rewrite that here, but it'd be -2 times column 4. Of course, that'd be -2 times each of these entries, so that you would get, well, okay, maybe I'll write it here, right? If I wrote -2 times this column, what would I get? I would get, like minus 0.0431 minus 0.0050 minus 0.0221 minus 2.0019 and minus 0.0220. Now, why shouldn't I be too worried about these minus entries? Well, if the external demand in sector 4 decreases by 2, then of course it makes sense that I now need to scale back production in these sectors in this way, right? Here I'm scaling back production in sector 4 by more than 2, and that makes sense, because now not only do I need to make less of that product, but I also need to make less of product 4 for the other sectors, right? So this is the idea, okay? And it's very useful. This fact 3 that we had here was very useful. It means that now I can use this to compute how this impacts production based on any. I can scale my external demand by whatever. It doesn't just have to be increments of 1, obviously, so I can scale it by whatever here. Okay. Now, what this means is that oftentimes, right, the questions that you are going to ask about how production needs to change doesn't need to know every single entry of this thing, okay? So it doesn't need to know every single entry of this thing. You might have a question specifically about a single entry, right? Might be the thing that you care about. And so if that's the case, we don't need to compute the whole inverse. We actually just need to compute this entry. So then how do I do that? How do I compute just the entry? So here's the thing, right? So note, computing a matrix inverse can be intensive, we'll say. Now, you might scratch your head at some of these things where we're nervous about computing matrix inverses, or we're nervous about, but the thing you have to remember is that when you are dealing with these things practically, right? Like if we're talking like you're dealing with something in cryptography, or you're dealing with a model matrix for a model in many, many real world examples is going to be absolutely gigantic. Okay, so the size of the matrix is going to be absolutely absurd. And on account of that, a lot of the computationally, a lot of the things that you learned to do by hand to help you understand like what is going on under the hood um, is not going to be super useful computationally because it's just too intensive. So perfect example, I think I told you this on day one in the lecture, is determinants, right? So you compute determinants by cofactor expansion, right? And I'm about to refresh your memory on what a cofactor is. You compute determinants based on cofactor expansion by hand to help you understand algebraically what a determinant is doing, how a determinant is computed. But computationally, using cofactor expansion is really terrible because the number of operations you have to do just blows up. It's awful, right? It involves a factorial. It's just terrible. So computationally, that would be awful for a 200 by 200 matrix. And a 200 by 200 matrix is not even that big for some things. For some model matrices, 200 by 200 is maybe not even as big as it gets. So that's what I mean by intensive here. You may be dealing with a matrix that's absolutely gigantic. Okay. So we would very much like to compute the entries entry by entry if we can. So it is nice for this reason to be able to compute I minus m inverse entry by entry. Recall some definitions, okay, so that we can do this. So quick definition, recall. If A is an n by n matrix, then the ijth cofactor is the following. We write this as C sub ij. This is minus 1 to the I plus j times the determinant of A sub ij, where A sub ij is the n minus 1 by n minus 1 matrix obtained from A by deleting its ith row and jth column. This is ringing a bell. It's minus 1 to the I plus j. This tells you, right? So determinant is always an alternating sum. So determinant's always an alternating sum, so this just ensures that this sum, if we're summing over a row or a column in cofactor expansion, so cofactor expansion is just noticing that I can sum these over either rows or columns, and this computes the determinant of A. Okay, so this just ensures that whether you're summing over rows or columns is an alternating sum. Maybe it's plus minus plus minus, maybe it's minus plus minus plus. In either case, it is an alternating sum. Okay. Now, there is a fact. This is called the adjugate formula. If you happen to be looking in like an older textbook, or I guess potentially if you're looking somewhere online, the thing I'm about to write would also be called a classical adjoint, but there's a reason to avoid that terminology because adjoint usually means something slightly different. So, but you might see this referred to as classical adjoint, but I'm going to call it the adjugate. So this is called the adjugate formula. Let A be an invertible. Let A n by n be invertible. Then there is a formula for A inverse, which is 1 over the determinant of A times the adjugate of A, where the adjugate of A, maybe I'll write it here since I have more room. This is called the adjugate. The adjugate of A is the matrix that contains the cofactors like this. And you might notice that the role of column and row in the indices has been changed here. So in order to make sure that you understand that, I'm going to write it again here. But this is how the adjugate is computed. Before I go further, what I'm going to say is, recall, or maybe you haven't seen this, so maybe this is your first time seeing it, in which case you're going to recall it now after I write it. Recall, if A is 2 by 2, we know that A inverse is 1 over AD minus BC times, we'll say, could have written this more efficiently. We'll say that my 2 by 2 matrix looks like this, A, B, C, D. Well, it turns out that this is actually just the adjugate formula. It's just for a 2 by 2, the adjugate, the cofactors are just these single entries here. So this is the adjugate of A. This matrix is the adjugate of A, and you can compute that yourself if you like. So if you ever wondered where this formula came from and you asked yourself whether or not there's such a formula for a 3 by 3, absolutely there is. It's just for a 3 by 3, it is not as nice, and you have to compute 9 cofactors, which can be done, and in many cases is a lot simpler than going through the process of actually finding the inverse. But that's, that's still like 9 separate computations, and you got to compute the determinant. Like, that's fine and all, and computationally, handling this with a computer is very nice. But you see why we do this for the 2 by 2 all the time, but for a 3 by 3, maybe we don't resort to this, even though we absolutely could, and it's fine. Okay, so this is where we get the 2 by 2 formula. So now let's see what this means for the inverse, or for the ijth entry of A inverse. So this is going to be, by the adjugate formula, 1 over the determinant of A, that's not changing, times the thing to note in this adjugate formula is that the ijth entry of this thing is C sub ji. That's what I meant by the role of row and column is swapped here. So it's like you had the cofactor matrix, right? So you had the matrix containing the ijth entries, the ijth cofactors, and then you transposed it. Okay, that's what's going on here. Now, writing out like what this is, of course, this is 1 over the determinant of A. But remember, cofactor is exactly this thing. So this is C sub ji, so this would be minus 1 to the j plus I, that doesn't matter that much, times the determinant of A sub ji, which again is just the matrix I obtained from A by deleting the jth row and ith column. Okay, so that the ijth entry of A inverse can be thought of as minus 1 to the j plus I times the determinant of A sub ji over the determinant of A, which gives us a nice way to compute these entries one at a time in case we don't want to compute the entire inverse, right? Now, if I wrote this in a slightly more expanded form here, this is me saying A inverse can be thought of as 1 over the determinant of A times the matrix, which in the top left, right, is first row, first column. This is plus the determinant of A11. Then this would be minus the determinant of A21. Then this would be minus the determinant of A12. This would be plus the determinant of A22. This would be plus the determinant of A31, and so on, plus the determinant of A13, so on, so on. I'm not going to write all those, but this is how it would be. This is a more convenient way of writing it, obviously. Okay. And so I think rather than start going through this example and having to stop in the middle, I'm just going to wait until tomorrow's lecture to fully cover this. So I said I would go through all of the remaining input-output model stuff, but I'm going to have a little bit more to do. I'm going to have maybe like 20 minutes of material to do in tomorrow's lecture, and then we'll truly be done, but we will have done literally everything there is to do or that we cared about for this. So I think this is a good stopping point today to get through this material. And so I think what I will do is stop here, and I'll resume tomorrow, and we'll finish this and then start on our next topic. Your homework is due tomorrow. It doesn't include any of this Leontief input-output stuff. That'll be on your next homework. So after your first homework is due, I'll assign second homework, obviously, to be due probably next Monday, but I'll let you know when I assign it. And I'll let you know about the office hours session in case you have questions about things. So be on the lookout for Elm's announcements. But anyway, I think that is all for today. So I'll stop here, and I will see you all tomorrow.